2, 3 lies in the first quadrant, whereas 2, -3 lies in the fourth quadrant. It is exactly mirror image to each other. Hence, we can also represent the conjugate of a complex number in the argand plane by the line segment of complex number with the x-axis, which is called as an argument or amplitude of a complex number. Cos is negative, so therefore we will take it as pi minus pi by 4, because for pi minus pi by 4 cos becomes negative. Hello everyone, a warm welcome to one and all. This is Ashruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. In this session, we are going to study about the argand plane as well as the polar representation of a complex number. So, what is this argand plane? So, any complex number can be represented in the form of an ordered pair, which can be a point in the Cartesian system. So, for example, if we have a complex number in the form of 3 plus 4i, we can write it in the ordered pairs as 3, 4, and 3, 4 again can be expressed in the form of a plus ib. Suppose if we have x plus iy as a complex number, then I can write x, y as a point in the xy plane, which is a coordinate system. And here, since we have x as real number and iy is an imaginary part of a complex number, we take the x-axis as real axis and y-axis as the imaginary axis. That is, x-axis represents the real part of the complex number, whereas y represents the imaginary part of the complex number, and hence we can write it in the form of a coordinate form in terms of x, y. And what does here mod z represent? We know that the distance of any point from the origin is square root of x square plus y square. Suppose if you have p of x, y as a point and O is the origin, the distance of point from the origin is given by using the distance formula. It is square root of x square plus y square. But modulus z of the complex number is also square root of x square plus y square. Thus, in this plane, mod z can be taken as the distance of a complex number, which is represented in the form of point p of x, y, which is from the origin. Hence, the distance from the origin to p is nothing but mod z here, whose value is square root of x square plus y square. And this is called as the argand plane, or sometimes we also called as the complex plane, where we'll take x-axis as the real axis and y-axis as the imaginary axis of a complex number. Next, here we have an argand plane. Another application of an argand plane, we can represent the conjugate of a given complex number. Suppose, consider we have a complex number 2 plus 3i. Then what is the point here? It is exactly 2, 3. What is the conjugate of this number? It is 2 minus 3i, whose coordinates can be 2, minus 3. So, we clearly px, y is exactly the mirror image of qx, minus y, and the distance from O to P is also mod z, O to Q is also mod z. That is, since distance is always positive, the square root of x square plus y square is here the same square root of x square plus y square, whereas the point, it changes. 2, 3 lies in the first quadrant, whereas 2, -3 lies in the fourth quadrant. It is exactly mirror image to each other. Hence, we can also represent the conjugate of a complex number in the argand plane. Now, let's take few problems on complex number here. If z1 is equal to 2 minus I, z2 is equal to 1 plus I, find the modulus of z1 plus z2 plus 1, z1 minus z2 plus 1. So, this is based on the algebra of complex number, as well as then we need to find out the modulus of the given complex number. Let us take z1 plus z2. So, when I say z1 plus z2, it is 2 minus I plus 1 plus I plus 1. Z minus z2 means 2 minus I, minus z2 means minus 1 minus I. So, when you are writing minus of the given complex number, change the value of the complex number, minus if it is plus, plus if it is minus. Then we have here plus 1. So, here minus I plus I get cancels. 2 plus 1 plus 4 becomes 4. And here minus I becomes minus 2i and minus 1 plus 1 get cancels. We have 2 minus 2i here. So let me solve this. So we have 2 minus 2i on the denominator. Let us make it rational number in the denominator. So multiply with its conjugate. So then we will get it as 4 into 2 plus 2i. And here again it is in the form of a minus ib, a plus ib, which can be written as a square plus b square for the complex number. So therefore here value of a is 2 square, which is 4. Value of b is minus 2, which is again 4. So you will get this as 4. You can also take 2 as a common factor here. Again you will get into 2, 1 plus I divided by 4 plus 4 is 8. 4 2s are 8, 8 get cancelled. So the value is equal to 1 plus I. So now we need to find the modulus of this. So this complete thing is solved and we got the value as 1 plus I. So let's take the modulus of 1 plus I. So modulus of 1 plus I is square root of a square plus b square. Hence the value is equal to root 2. So therefore modulus of z1 plus z2 plus 1 divided by z1 minus z2 plus 1 is equal to root 2. Next question. Find the modulus of 1 plus I by 1 minus I minus 1 minus I by 1 plus I. So let me take here, let z is equal to 1 plus I by 1 minus I, 1 minus I by 1 plus I. Taking LCM, so we will get this as 1 plus I whole square, 1 minus I whole square, which is 1 minus I, 1 plus I. So if you expand this, you will get this as 1 square is 1 plus I square is minus 1 plus 2i. Next we have 1 square is 1 plus I square is again minus 1 minus 2i we will get. Whole divided, here it is a square plus b square, so 1 square is 1 plus b square, again it is 1 square is 1. So next here we have 1 minus 1, 1 minus 1, 2i, minus of minus 2i becomes plus 2i, so 4i divided by 2. So when it get cancels, we will get the value as 2i. So now we need to take the modulus of this. So therefore this is our z now. So therefore modulus of z, which is nothing but modulus of 2i, it's a purely an imaginary complex number. So therefore it is square root of 2 square, whose value is equal to 2, because it doesn't have any real part there. Next, we have a polar form of complex number. So I already told you that any complex number in the form of x plus iy or a plus ib can be represented in the system of coordinates as x comma y or a comma b, and that is called as argand plane. So we have the another form of representing a complex number, that is the polar form. So consider x and y axis here. Let theta be the angle created by the point or by the line segment OP. Okay, so angle XOP is equal to theta here, and the distance is here r, and the point P of x comma y can be represented in terms of r and theta. Here r is again the modulus. Instead of modulus z, we are representing it by using r, and theta is called the angle which is called as the amplitude or argument of a complex number. That is the angle created by the line segment of complex number with the x-axis, which is called as an argument or amplitude of a complex number. And the polar coordinates are written in the form of p r comma theta, and r will use by the same method, that is we take r as a square root of x square plus y square, and theta can be found by two equations, that is x is equal to r cos theta and y is equal to r sin theta. So here the coordinates x comma y can be taken as r cos theta, r sin theta. So in the place of x and y, we can replace it by r comma theta. So thus z is equal to r cos theta plus I sin theta represents the polar form of a complex number. So they are one and the same. So they are one and the same equivalent. Z is equal to x plus iy is same as r cos theta plus I sin theta. So when you take the real values along with the angle, so here sin theta cos theta along with r will give you a real number x and y. Hence, they are equivalent to each other. Thus, this is the complex form and this is the polar form of representing a complex number. Now, here in the form of polar form of a complex number, as I said, r is nothing but mod z. It is same as in case of your complex form or complex number form. It is same, that is the modulus, and theta is called as the argument of z, or sometimes it is also called as amplitude of z. Remember, the condition of theta here always it lies between minus pi to plus pi, that is minus 180 to 180 degree. That means it is the principal value of your tan theta. We can take it in the form of tan theta is equal to y by x. So, depending on the value of y by x and the real value, we can find the value of theta based on whether it lies in the first, second, third, fourth quadrant, as you have done in the principal solutions of trigonometric functions. Now, to find theta here, when z is purely real, what happens when z is purely real here? Then the point lies on the x-axis. So, therefore, if x is greater than 0, the theta is equal to 0. And if x is less than 0, the theta is equal to pi. Like, suppose you have purely real means the numbers will be in the form of z is equal to 1, z is equal to 2, z is equal to 3. So, therefore, the only you have x coordinates and y coordinate is completely 0. Suppose you have a x coordinate on the positive side of the x-axis, then the angle created by this point with the x-axis is 0. So, therefore, that is theta is 0. Suppose the point is here, then the angle created by this line segment of point is theta is equal to pi. Hence, if x is negative, theta is pi, and if x is positive, theta is 0. Next, we have when z is purely imaginary. When I say purely imaginary, the point lies on the y-axis. Suppose the point lie on the positive side of x-axis, then the angle of this point with the line segment along with x and y-axis is 90 degree. So, therefore, theta is equal to pi by 2. If point lies on the negative side, then we take the clockwise direction and we'll measure the angle as minus 90 degree. That's why we take it as minus pi by 2. Next, other than those two conditions, if the point lies anywhere on the x and y axis, then we can take tan alpha as tan theta, or tan theta here it can be represented using by modulus of y by x. And depending on the value of alpha here, we have theta is equal to alpha if it lies in the first quadrant, pi minus alpha it lies in the second quadrant, pi plus alpha, or we can in tan we can take it as alpha minus pi or minus alpha in the fourth quadrant. So, these are the values we should take for the tan angle if the alpha lies in different quadrants. Next, find the modulus and the arguments of the following. So, here we are supposed to find out the r and theta for the following complex number. So, we have here z is equal to 1 plus I. Assume it in the form of z is equal to iy. So, what is the value of x here? 1, and value of y is 1. So, therefore, r is square root of x square plus y square, whose value can be taken as root of 1 plus 1, which is equal to 1. Now, we need theta. So, we know the conversion that x can be taken as r cos theta and y can be taken as r sin theta. So, here x is nothing but 1, r is nothing but root 2 here. So, root 2 cos theta, and y value is 1, r is again root 2 sin theta. So, now here we have 1 by root 2 cos theta value and 1 by root 2 for sin theta value. Now, for which measurement of an angle, cos function is 1 by root 2 and sin function is 1 by root 2. It is for 45 degree or pi by 4. So, therefore, theta is equal to pi by 4 here. So, this is how we will find the modulus. So, this is one way of finding angle. So, we have also have the formula, that is tan theta is modulus of y by x here. So therefore, value of y is 1, x is 1. So we will get it as 1. So tan theta is equal to tan pi by 4. So therefore, theta is equal to pi by 4. So this is another way of finding the angle. Next we have root 3 minus I. So here x is equal to root 3, y is equal to minus 1. So therefore r is equal to square root of x square plus y square, which is nothing but root 3 whole square 3 minus 1 whole square 1. So we will get it as root 4. So therefore r is equal to 2. That is the modulus is 2. Next we will find out theta. Can take x is equal to r cos theta and y is equal to r sin theta. So value of x is root 3, r is 2 cos theta. So this implies cos theta is equal to root 3 by 2. And here we have y as minus 1, r as 2 sin theta. So we will get sin theta is equal to minus half. So here theta can be taken as pi by 6 because we have root 3 by 2 and here we have minus half. So here sine function is negative, so we can take theta in the form of pi plus pi by 6. Because for pi plus pi by 6 we will get the solution as minus half. So this is equal to 7 pi by 6. Or we can also write it as minus pi by 6. Next question. Convert the following complex numbers into polar form. So that is, we need to write this in the form of z is equal to r cos theta plus I sin theta. So let's take x is equal to minus 1, y is equal to 1 here. Then r is square root of x square plus y square, which is equal to root 2. Next we have x is equal to r cos theta and y is equal to r sin theta. So we will get x as minus 1 root 2 cos theta and 1 root 2 sin theta. So we will get cos theta as minus 1 by root 2 and sin theta as 1 by root 2. So 1 by root 2 of sine and cos is same for angle 45 degree, that is pi by 4. But since this cos is negative, we will take theta as minus pi by 4. Cos is negative, so therefore we will take it as pi minus pi by 4 because for pi minus pi by 4 cos becomes negative. Therefore, we take theta as 3 pi by 4. If sine is negative, we will take it as pi plus pi by 4. But since cos is negative, we will take it as pi minus pi by 4. Because sine pi plus pi by 4 is negative, cos pi minus pi by 4 is negative. So therefore, depending upon the sign, whether cos is negative or sine is negative, we will take theta. So in the previous problem, we have taken sine as negative value. So we have taken in the pi plus theta form. Here cos is negative, that's why we will take it in the form of pi minus theta. So therefore our theta is 3 pi by 4 here. So now the polar form is z is equal to r cos theta plus I sin theta. So value of r is root 2. So cos theta value is 3 pi by 4 plus I sin 3 pi by 4. Just substituting the value of r and theta. This is the polar form of a given complex number. Next we have root 3 minus I. So again we can directly take r is equal to root 3 whole square plus minus 1 whole square under the square root. So r is equal to 3 plus 1, which is root 4. So therefore r is equal to 2. Next we have x is equal to r cos theta, y is equal to r sin theta. So here value of x is root 3 2 cos theta and here minus 1 2 sin theta. So we have cos theta is equal to root 3 by 2 and sin theta is equal to minus 1 by 2. So cos pi by 6 is root 3 by 2 and sin pi by 6 is 1 by 2. But here sin is negative, therefore we will take theta as pi plus pi by 6. whose value is 7 pi by 6. Hence, we can write the polar form using r and theta as z is equal to r cos theta, that is 7 pi by 6 plus I sine 7 pi by 6. So next we have 1 plus I root 3. So r can be taken as x square plus y square under the square root. So therefore r is equal to 2 again because it is 4. Next we have x is equal to r cos theta, y is equal to r sin theta. So clearly value of x is 1, 2 cos theta. This gives cos theta is equal to 1 by 2. And here we have root 3 is equal to 2 sin theta. So therefore sin theta is equal to root 3 by 2. Both are positive and clearly for pi by 3, cos pi by 3 is 1 by 2 and sin pi by 3 is root 3 by 2. So therefore theta is equal to pi by 3. And hence the polar form is 2 into cos pi by 3 plus I sin pi by 3. This is the value. If you want to verify this whether they are equivalent, we know cos pi by 3 is 1 by 2, sin pi by 3 is root 3 by 2. So here 1 by 2 plus I root 3 by 2. So 2 multiplies with 2 cancels here. We will get back the same result as 1 plus I root 3. So this is how we will convert the complex form into polar form. We'll meet you in the next session. Until then, keep watching, keep learning, keep exploring. Thank you.